back. Remember, we're taking apart a list of 5 ways that we know from paleoclimate studies and so on have caused climate change in the past, and we're going to figure out, can we attribute any of the current climate change to these factors? We already took apart continental drift and largely determined that that can't be responsible for the observed climate change. How about changes in the sun? Now, to understand this stuff, we need to have a term here, the solar constant. The solar constant is an awkward term because the solar constant is not a constant. It is, though, just the amount of shortwave radiation that reaches the top of the Earth's atmosphere from the sun. It's a combination of how much radiation the sun is emitting and how far away the Earth is from the sun at any given time. I don't know why they stuck with this weird term, the solar constant, when it's clearly not a constant. Now, if we're going to be focusing at the present time on the sun, you can see we can move on the next part of the list to the Earth's orbit. So for now, we're just focusing on the sun's output itself. If the sun is brightening, we would expect the solar constant to increase, and that seems like that should make the planet warm. And we do know that the sun's output changes on many different timescales. There's lots of things going on in the sun. For example, astronomers can tell us that over the course of the last 5 billion years, billion with a B, we know that the total output of the sun has increased by about 30%. It has to do with the way in which the ratios of hydrogen to helium in the core of the sun have been changing, and the temperatures that have to change in order to keep fusion going inside of the sun, and so on. We know that there's been a 30% increase in the output of the sun, and the sun is going to continue to increase in output for at least the next few billion years. But that's a long time. Now, just since the 1970s, we have had satellites in space dedicated just to measuring, actually spacecraft, not necessarily satellites orbiting the Earth, but we have a number of satellites at the present time included that are monitoring the output of the sun. And in fact, we can make plots. This is very similar to one of the plots that's in your textbook. We can see that there are changes in the amount of radiation being received at the top of the Earth's atmosphere from the sun. In fact, it has a cycle to it of about 11 years. This is the so-called sunspot cycle. The sunspots themselves are slightly cooler areas on the sun. Sometimes there's more of them, sometimes there's less of them, but the more of them there are on the surface of the sun, the less radiation the sun is giving off. And you can see there is a couple of different ways of measuring such things, but you can see that there is a 11-year cycle to the amount of radiation the sun is giving off, but the difference isn't all that big. It's about 0.1%. The climate of the Earth does not meaningfully change based on an 11-year cycle. The thermal inertia of the ocean just isn't that, is so large that it just can't respond to changes that fast. I liked the analogy that was in the textbook where they were saying, imagine you put a big pot of water on the stove and you turn the stove on, turn it off, turn the stove on, turn it off, just keep flickering it on and off. And, well, I suppose if you had sensitive enough instruments, you could actually see the temperature of the water go up and down, 1/1000th of a degree for each of these little flickers on and off of the stove. But realistically, in no meaningful way was the temperature changing. And the same is true of the Earth system. 11 years is just too slow for these very small changes in the energy balance of the Earth to show up. The ocean barely has a chance to start warming during the warm 5.5 years of the solar cycle before the colder 5.5 years comes and it starts losing that same amount of heat. It's lost. We don't have an 11-year cycle to the Earth's climate. Now, in order for the sun to be responsible for this recent warming that we've actually seen in the last, few decades or whatever, there would have to be a long-term increase in the solar constant. We'd actually have to be seeing with our satellites that we've had and so on that, since 1970s or something like that, the sun would have to be getting warmer and warmer and warmer overall. And there's absolutely no evidence of that whatsoever. No satellite records anything like that. No other mechanism, no models of how the sun works, no other forms of observation. There is literally no evidence whatsoever that since the 1970s, when we have had dedicated spacecraft doing such measurements, that there's been any net increase in the output of the sun. But of course, that is just since the 70s. What about before the 1970s? We had a lot of warming since the Industrial Revolution, and, before the 1970s, what can we say? Well, before we would have spacecraft up there actually measuring the output of the sun, we would be depending on other ways of determining what the output of the sun was. For example, scientists have actually been observing the sun and counting and measuring the size of sunspots for about 400 years. and the number of sunspots is very closely related to the output of the sun, so we can actually estimate the output of the sun from that. There's also certain isotopes that form in the Earth's atmosphere and in the ocean and so on, depending on the output of the sun, and we can measure those out, those isotopes in like trapped bubbles, pockets of air in ice cores and things like that. There are ways that we can get at estimates of the output of the sun in the past few hundred years as well. And when you actually do that, you do find that there is some possibility that the sun has actually increased in temperature since like roughly, I'm sorry, in terms of the solar constant, since about 1750. 1750 is right around the end of the Maunder minimum, where there was a long period of time with low solar activity, and there is some reason to say that in the last like 200 years or something like that, this total amount of power emitted by the sun has increased. And we can actually put quantification on that. We can actually, determine based on how many sunspots were observed, how many that would be, and we end up with a true radiative forcing that should be making the planet warmer, but it's about 1/10 the size of the radiative forcing of greenhouse gases. Okay, well that's why we have science, is that we can put numbers on these and we can figure these things out. Yes, the sun has been outputting more energy, on the other hand, way less than the ways in which we have radiative forcing based on things like carbon dioxide and methane. Okay, so if we were talking about the solar constant, which is the total amount of radiation received at the top of the Earth's atmosphere, then part of that is how much the radiation the sun is giving off, but the other part is about how far the Earth is from the sun. And there are changes to the Earth-Sun distance. It comes to us from the fact that the shape of the Earth's orbit changes. There's about a 100,000 year cycle to the ways in which the Earth's orbit changes. For about half of that 100,000 year cycle, the Earth's orbit is somewhat more oval-shaped, more stretched out. The right word is more eccentric. The eccentricity of the Earth's orbit is greater, like is the picture on the left there. And then for the other half of the 100,000 year cycle, for about 50,000 years, the Earth's orbit gets almost completely round. Why does this happen? It has to do with perturbations to the Earth's orbit that happen based on the gas giants, mostly Jupiter. Over the course of about a 100,000 year cycle, Jupiter makes small changes just by gently tugging on the Earth's orbit at each point along the way that sometimes makes Earth's orbit a little more stretched out, more eccentric, and sometimes makes the Earth's orbit less eccentric and more round. Which is interesting, but there's actually a net effect to Earth climate. The more eccentric the orbit gets, the more oval it gets, the average Earth-Sun distance gets bigger. That's because of the way a planet goes around in orbit. The part of the orbit that is farther from the sun is not only farther from the sun and getting lesser energy, but the planet moves more slowly while it goes to that orbit. The part of the orbit that's closer to the sun, the planet moves much quicker. So as the planet goes around its orbit, it spends most of its time on the part that's farther from the sun and very little of the part that's close to the sun. If you need to convince yourself of that, think about a comet. Comets are in highly eccentric orbits. They spend 99.9999% of their time way out in the outer solar system, just a dead frozen ball of gas, and then they whip around the sun over the course of a few weeks. Okay, and so they spend a very short period of time close to the sun and an enormous amount of time farther away. Same with the Earth. If the Earth is more eccentric in its orbit, it spends more of its time farther from the sun than close to the sun. Overall, the planet is cooler when the orbit is more eccentric, and overall the planet is warmer when the orbit is more circular. And the difference is not all that small. It's about 0.5 watt per square meter. That's a pretty good radiative forcing. That seems like that could be enough over long periods of time to start feedbacks and so on. They're going to create ice ages and so on, and in fact we'll see that that's the case. I mean, actually though, changes in the Earth's, like the shape of the Earth's orbit, the eccentricity of the Earth's orbit, are actually only one of 3 ways in which the orbit can change based on gentle tugs from the gas giant planets. There's also, like for example, a 23,000 year cycle to the time of year at which Earth experiences perihelion. Perihelion is the date at which the Earth gets closest to the sun in its orbit. And again, that can have an implication for climate, depending on like which hemisphere has more continents and so on. This can have a very big impact on climate. Again, it has a 23,000-year cycle. There's also a 41,000-year cycle that has to do with the obliquity of the Earth, or rotation. Obliquity refers to the tilt of the Earth's axis. How much the Earth's axis is tilted slowly changes over the course of a 41,000-year cycle, and this changes the seasonality. The less tilted the Earth's axis is, the smaller the difference is between summer and winter. When the Earth's axis is tilted more, there's a bigger difference between summer and winter. This is about changes then in the obliquity of the planet. Again, it's just internal mechanics of how the orbits of all the planets and so on interact with each other. Let me just see here. All this stuff can be computed back millions of years into the past. And paleoclimate records surprise us here by showing nearly perfect agreement between when ice ages happened and when these changes in the Earth's orbit were happening. When the planet should be colder because of changes in the Earth's orbit, the planet is an ice age. When the planet should be warmer, we're in an interglacial period. Taken together, this pattern of changes in the Earth's eccentricity, the obliquity of the axis of the Earth, and the date of the perihelion, taken together, this whole set of cycles is called the Milankovitch Cycles. Milankovitch was a Serbian mathematician a long time ago who figured all this stuff out and made the connection to climate and so on. And it's a real thing in paleoclimate. I mean, this is important for like when ice ages have happened in the past and so on. Maybe they're responsible for climate changes now. Well, we can actually figure this all out, and we can see that the Milankovitch cycles cannot be responsible for the climate change we're observing now. They're much too slow. Even as the Earth's axis is slightly changing, even as the Earth's orbit is slightly changing, even as the date of perihelion slowly shifts and so on, all of these changes are much too slow. Now, all of those changes will at some point in the future be contributing towards a cooling of the planet and eventually or at least leaning towards the formation of an ice age. But in fact, modern anthropogenic increases in greenhouse gases and other radiative forcings have actually precluded the formation of any ice age for at least another 100,000 years in the future. The Milankovitch cycles will not be sufficient to make the planet cold enough to form another ice age for at least another 100,000 years, simply because we've put so much greenhouse gases in the atmosphere and they won't be gone. Even 50,000 years from now or something like that, when maybe changes in the Earth's orbit will be trying to produce ice ages and so on, there'll still be too much greenhouse gases in the Earth's atmosphere. I think that's fascinating. All right, before we move on to part 3 of the lecture, let's do 2 more questions real quick. Question 3. Overall, the planet tends to be cooler during periods in which the orbit of the Earth is blank eccentric, more or less. All right, just make a choice from those 2 and get a little feedback before you move on to question 4.